to do some physics problems for you here, starting with number 19. The first couple of these, I know you just did some impulse momentum notes. The first two are just about momentum, and then the impulse stuff starts with number 23. So just a heads up there. I guess you've tried these already, so you probably have some sense of that. So number 19, I got a truck with a mass of 2,100 kilograms traveling north at 41 kilometers per hour. And then it turns east and accelerates to 51 kilometers per hour. What's the change in the truck's kinetic energy? What are the magnitude and direction of the change in its momentum? Okay, so for part A, the change in kinetic energy, that's kinetic energy final minus kinetic energy initial, and that's going to be equal to 1/2 m. Oh, I guess I got to change these if I'm going to do kinetic energy. I got to change them to the right units. Hold on a second. So 41, that's kilometers. So I need to multiply by 1,000 and divide by 3,600. So that is 11.4 meters per second, and this is 14.2 meters per second. Okay, sorry about that. So I just have the 1/2 mv squared minus the 1/2 mv squared. So 1/2 m v squared minus I get about 75,000 joules there for that change in kinetic energy for part A. For part B, here's the point of these first couple problems. Momentum is a vector, right? If momentum is equal to mass times velocity, if velocity has a direction and you multiply it by mass, which is a scalar, which is called a scalar, you like just scales the velocity up or down, right? It doesn't change the direction of it, it just makes it longer or shorter. If you multiply a vector by a scalar, you get another scalar, right? All right. So that means that when we do change in velocity here, that we got to respect the directions of these things. So this is not just going to be like the magnitude of this minus the magnitude of this. You subtract two vectors, you got to put them in component form. You got to do the thing, right? We know how to do vectors. So we got east. It shouldn't be too hard because I have because these are just, if we just use the typical north, south, east, west, that north is the positive j direction and this is the positive I direction. Then I have mass here, and then this final is 14.2 in the positive I direction minus this one. They only just have one I or j, right? Minus 11.4 in the j direction meters per second. And so if we want the magnitude of this and the direction of this, multiplying by this isn't going to change the direction. The magnitude I could just Pythagorize those and then scale it up. So, or you can distribute that however you want to deal with this. 14.2 squared plus 11.4 squared. So the hypotenuse of this little triangle here would be 18.2, and then multiplied by 2100 is about 38,000. I think I forgot to talk in the notes about the units for momentum, kilogram, meters per second, and it doesn't have a special name. Kind of unusual little example in physics about how something did not get a special name. Because, kilogram meters per second squared, that's a Newton. Kilogram meters squared per second squared, that's a joule. Kilogram meters squared per seconds cubed, that's a watt. This is just kilogram meters per second. So what else do we want? We want the direction also. So tangent inverse of rise over run, 11.4 over 14.2 is about 39 degrees, and that is going to be positive, negative, so I'll say, let's see, south of east, fourth quadrant. All right, let's check those, see how we did. 75,000 joules, 38,000 kilogram meters per second, 39 degrees south of east. Great. Okay, so 21. A 300-gram softball has a velocity, great, ironically named object. You ever felt a softball? Not very soft. Pretty funny name for it. A 300-gram softball has a velocity of 15 meters per second and an angle of 35 degrees below the horizontal. So like this. 15 meters per second. Just before making contact with a bat, what's the magnitude of the change in momentum of the ball while in contact with the bat if the ball leaves with a velocity of 20 meters per second vertically downward? And 20 meters per second horizontally back toward the pitcher. So if it's coming in this way. So that's our second option. All right, well, we need these in IJ components because we just need to do this. So this is not hard to do. They just want the magnitude. They don't want the angle. So mass times change in velocity for this one. So the final velocity here for part A would be negative 20j minus the initial velocity is, in component form, that would be 15 times the cosine of 35 is 12.3 I minus 15 times the sine of 35, 8.6j. So I got minus 20j, that's my final here, and then minus the initial, which is 12.3. God, I keep doing that. Stop it. Minus 8.6j. And remember, you can only combine the like things there. That actually is a j. And what do I have here for the j's? I have minus 20 minus 8.6 minus 20 plus 8.6 equals times 0.3. So that's, I don't know why I did the j's first. That's minus 3.42 j. And then the I, it's just this 12.3 times 0.3 minus 3.7 I kilogram meters per second. Oops. And I want the magnitude of that. So I'm going to Pythagorize those. That's 3.7 squared plus 3.4 squared, about 5.0. Okay, and then for part B, you're going to do the exact same thing, but and the final is the same. Sorry, this initial is the same rather, but this time it's going to be, this is minus 20I is that final velocity. And we should think that, like, if it's coming in this way and it gets sort of like accidentally, like a bad bunt or something, down, and then if it gets, this magnitude should be bigger. If you change the momentum from this way, like to back the other way, this should come out to be bigger. If it's going to match up with our intuition about things, which it should. Okay, so here, now I've got minus 20 minus 12.3 times 0.3. That's minus 9.7I. And then the j component is plus 8.6 j kilogram meters per second. And that's has a magnitude of 9.7 squared plus 8.6 squared is about 13. Let's checky those answers. 13. Why is there only one? Oh, 13. Why am I checking 13? This is 21. Because I got 13 as an answer. They have 10 for this, so I did something wrong. Let's see. Did I forget to multiply? I forgot to multiply this by 0.3. That's what it is. So let's just assume that they have the right answer in the back of the book. That should be 0.3 times 8.6. Oh, that's 2.6. Yeah, that looks right. Sorry about that. Easy fix. And let's see, got some fresh paper around here somewhere. I'll find some. Here's some. So that brings us to number 23. Until the 70s, Henri Lamotte excited audiences by belly flopping from a height of 12 meters into 30 centimeters of water, assuming that he stops just as he reaches the bottom of the water and estimating his mass. What do you think? Mass of this guy. There's a picture of him. He looks like a pretty skinny old man. I'm going to say 70 kilograms, something like that for some old dude. He stops just as he reaches the bottom, estimating his mass. What's the magnitude of the impulse on him from the water? So, impulse is equal to change in momentum. And I think the thing that we have access to here is not like the force and all that. It's this, right? We've estimated his mass. And how about his change in velocity? Well, his final velocity is 0, right? And his initial velocity is, well, if he's belly flopping from a height of 12 meters, a couple ways to do that, but the easiest way is to say that his gravitational potential energy at the top is going to turn into kinetic energy. So we've done this many times. So his velocity is going to be the square root of 2gh. So his final velocity, you could also do kinematics there, but I think this is easier. Square root of 2gh. So mass, final velocity is 0 minus about 15. So that 15 times 70. So the impulse on him is about, what is the negative sign? Well, if I said that his velocity was 15, that's down, so this means up. So upward, of course, that makes sense that should be the direction of the impulse. So it's about 1,000 kilogram meters per second in the up direction. Let's see what they have for an estimate. Yeah, they have 1,000 to 1,200. That's good. 25, a 1.2 kilogram ball. Excuse me for 1 second. They're coming. 25. A 1.2 kilogram ball drops vertically onto a floor, hitting with a speed of 25 meters per second. It rebounds with an initial speed of 10 meters per second. We want to know the impulse. Impulse is equal to change in momentum. And the change in momentum of this ball is mass times its change in velocity. The mass of it is 1.2 kilograms. And its final velocity is, let's say the up is positive. Its final velocity is 10 minus its initial velocity is 25 meters per second down. I've seen lots of students mess this up. You have to be super careful about signs. The change in velocity, if it's going from 25 down to 10 up, the change is not 15. The change is 35, because that direction matters. So 1.2 times 35, that's 42 kilogram meters per second. If you see in the back that some of the, remember that impulse equals change in momentum. Momentum has units of kilogram meters per second. This is like force times time, so units of Newton seconds are equal to kilogram meters per second. Sometimes you see this, sometimes you see this. Usually if we're focused more on momentum, we report this. In impulse, we report this, but they're equivalent, so they're both correct. If the ball is in contact with the floor for 0.02 seconds, what's the magnitude of the average force? Well, that's easy, as impulse is equal to average force times time. So the magnitude of the average force is just the impulse divided by the time interval. And I know the impulse here, 42 over 0.02. So that's about 2,100 newtons. Wouldn't it be cool to be in a band that was called Isaac and the Newtones? Get it? Like tones? Force in the negative direction of an x-axis is applied for 27 milliseconds to a 0.4 kilogram ball, initially moving at 14 meters per second in the positive direction of the x-axis. The force varies in magnitude, and the impulse has a magnitude. All right, I got to write some of this stuff down here. 27 milliseconds. That's 0.027 seconds. Mass of the ball is 0.4 kilograms. It's initially moving in the positive direction of an x-axis. Who says that? Come on. 14 meters per second. What's the ball's speed and direction of travel just after the force is applied? And what are the average magnitude of the force and the direction of the impulse? Okay, so I know that impulse is equal to change in momentum. I know the magnitude of the impulse. The force is applied in the negative direction. So the direction of the force and the direction of the impulse have to be the same. So that means that that's negative 32.4 here. Equals change in momentum. That's mass times change in velocity. I think that's what we're looking for right here, right? Remember, it was initially moving in the positive direction of an x-axis. So 0.4 VF minus 10 to the 5.6, right? And going to add that over here. So I've got negative 32.4 plus 5.6 divided by 0.4 is the final velocity is going to be negative 67 meters per second. Wow, that's a lot. Did I do that right? 27. Yep. They wanted the speed, so they're just reporting the positive version of that. And direction, it's in the negative direction. What are the average magnitude of the force and the direction of the impulse? The direction of the impulse we already talked about, it's in the negative direction. And the time interval, I just have to, if this is the impulse, impulse is equal to that force times time. And what are they asking for? The force? So the force is equal to impulse over time. So same thing that we did in the last problem, 32.4 divided by 0.027 is, 1,200 newtons. Oh, that's the numbers switched around there. So 1,200 newtons in the negative direction. And just glance back at 25, make sure I gave you good answers for that. I did. So we're good. There you go.